Hi, my name is Shahnaz. In this lecture, we will study regular functions on quasi-projective varieties. But before that, let us recall that the set OXP is the ring of regular functions on a neighborhood of a point P in X, where X is an irreducible F1 algebraic set, and it is given as, this set is given as this set consists of those rational functions f divided by g. They are the rational functions on x such that g at p is different from 0. So in last lecture we said that this ring is a local ring, but we didn't prove it. Now here we are going to prove it. So we have a proposition. So the ring OXP is the ring of the set of functions of the form rational functions of the form f divided by g, where g at p is different from 0. So the ring, this is a local ring. Now we say a ring is a local ring if it has a unique maximal ideal. So this ring is a local ring with unique maximal ideal. I mean m sub p, where m sub p is the set of all the elements, say q in kx, set of all rational functions such that q of 0 is 0, sorry, q of p is 0. So we have to prove the ring OXP is a local ring, and this is the unique maximal ideal. So the fact that this set OXP is a ring is clear. Now it remains to prove that this set M sub p is a maximal ideal, the only maximal ideal of OXP. Now for this, let us consider the evaluation map. So consider the evaluation map. Let us call this map EV at P. So this is a map from this set OXP to the underlying field, which is K, where this evaluation map takes, this evaluation map EV at P takes the function f and it evaluates this function f at P. So one can note that this map is clearly a ring homomorphism. So then the evaluation map at P is clearly a ring homomorphism. So now if we look at its kernel, so also the kernel of this evaluation map EV at P is the set of all regular functions at P in the set OXP such that the evaluation at P of f is the 0 of this ring, which is 0, which is the set of all regular functions OXP such that uh, f of p, because evaluation of f at p is f of p is 0, and this is nothing but the set, I mean the set MP. So this is clearly an ideal. Now to prove it is the only maximal ideal, it suffices to prove that the set M sub p contain all the non-unities, and that is if an element is outside M sub p, then that element has to be a unit. So we claim that this M sub p is the only maximal ideal of uh, OXP. So it suffices to prove, it suffices to prove this MP contain all non-unities in OXP. Now let us take some element H in OXP, but which is outside MP. So if we prove this H is a unit, that means MP contain all the non-unities of OXP. So if H is an element of OXP, so we can write H as, so we can write H to be the element F or G, where G evaluated LP is non-zero. So this is by definition of OXP, because OXP contain all rational functions of the form f divided by g, where g at p is different from 0. So, so if this is the case, since h is not in MP, that means h evaluated at p is non-zero. So since h is not an element of M sub p, this means h evaluated at p is different from 0. So this would imply, this is possible only, this would imply f of p is non-zero. Now if this is the case, we can define the inverse of h as g over f. So now take h inverse to be the element g over f. So this is clearly an element of OXP, since f evaluated at p is non-zero. So this means that h is a unit. So then clearly h is a unit, and hence MP contain all the non-unities of OXP. Hence M sub p contain all the non-unities of OXP. So that means this ideal is, I mean, this is same as the Jacobson radical. So thus MP is the only maximal idle of OXP. Hence, if we look at the quotient OXP modulo the ideal M sub P, then this is isomorphic to K because MP being maximum, so it is a field. Now the local ring at a point P contain information about the properties of X near P. We will see later that we can determine the tangent space and singularities of X at P from OXP. So this OXP, this encodes information, information about the properties of X near P. So let us make a remark here. So the local ring, I mean OXP, this encodes, this ring encodes information about the properties of X near P. Or for example, this ring, the local ring at P determines the tangent space and the singularities of X at P. Now we have one more result. So we have one more result here. So let us consider. So let X be an affine subvariety. So be a closed subvariety. Then the ring of local functions at X. So this is actually equal to the coordinate ring of X. So this is what we have to prove. So let us prove this. So one inclusion is obvious. So note that we can view AX as, so we can view AX as, so we can write AX to be the element of the form F over 1, where F is an element of AX. So this is clearly a rational function. So this is contained in Kx because this one, uh, one does not vanish at any point of X. So this is a rational function. So we can view AX as the, a subset of the rational functions at X. So one can see over here f over 1 is regular at x because the element of 1 does not vanish at any point of x. So therefore this ax is actually, this is contained inside the ring of local functions at regular functions at x. Now for the other inclusion, let us take some element in ox. So for the other inclusion, let us take some element, say h inside ox. So this h is an element of ox. Then by definition of this ox, for any point P in X. So then by definition, for any point, say P in X, we can write uh, this H as the class of F divided the class of I mean class of F over class of G for some polynomials F and G in uh, the polynomial ring in n variables. So one should keep in mind that this is a subset of I mean this is a subset of O X. It contain the regular functions at X, and so any element H in O X is of this form. So but there is one more condition, that this G does not vanish when evaluated at P. So with G of P different from 0. Now let us define a set J which contain all the polynomials in the polynomial ring in n variables x1 up to xn, such that if I look at this element H and I multiply the class of G here, so this element should this element must be an element of the coordinate ring of X. So note that the coordinate ring of XAX is the quotient ring kx1 up to xn modulo Ix, the ideal of X. So every element in AX is a coset. So now it is easy to prove that this J is an ideal, because if we have two elements, say G1 and G2 in H, then H dot class of G1 and H dot class of G2 in are the elements of X. So so is their sum and their product. Similarly, it is closed under the multiplication. So this is actually a subset of Kx, the rational functions, not the rational functions. So this is actually an ideal of the polynomial ring. So this is a subset of Kx1 up to xn. So this is an ideal in this ring, this polynomial ring. So this is clearly an ideal in the polynomial ring Kx1 up to xn. Now let us take some element. So now take some element, say t in the ideal of X. That means t vanishes at each element of X. So then if I look at the coset t plus I of X, so it is equal to I of X, because t is an element of I of X, or the class of t is same as the zero of the zero element of this coordinate ring, because this class of t is an element of Ax. Now by this property it says that the class of t is same as class of 0 in Ax, which is the quotient ring kx1 up to xn modulo Ix. So now t being same as the class 0 and 0 being the element of Ax. This means that this class of T is an element of Ax. So that is class of T belongs to Ax. Now, if this is the case, so is the element H dot class of T, and hence H dot class of T is also an element of Ax. Now, by definition, if H of class of T is an X, this means that this T is a polynomial inside J. Now, we choose this T inside Ix, and we proved that this T is in J as well. That means this Ix is a subset of J. So, hence, uh, this contains the ideal of X. Now, if this is the case, then the zero set of J is contained in the zero set of I of X. So therefore, zero set of J, this is contained in zero set of ideal of X, which is same as X. So zero set of J is a subset of X, but zero set of J is the empty set. Why? But zero set of the ideal J is empty. Why? Because for every point P in X we can find, so because for every point say P in X we can always find G in J such that G of P is not non-zero. We can always find G inside the ideal J such that G of P is non-zero. I mean there is no there is I mean at each point of X we can always find a polynomial inside J which vanishes at that point. So that means zero set of J is empty. Now if zero set of J is empty by null search, so this is given to be empty. So this is only possible if this zero set of if this J is equal to the whole ring. So this follows from the null search, or if J contains a unit, in particular if J contains 1. So thus by null search J contains 1. Now if J contains 1, thus so if 1 is in J, that means 1 times H times 1 is H times class of 1 is in AX. So thus H, which is equal to H times 1, is in AX. We chose this H inside, we chose this H inside O of X, and we proved this H is inside AX. So this means hence the ring of regular functions on X is contained inside the coordinate ring. So this means that these two rings are equal. Now uh, we want to define the regular functions on quasi-projective varieties. So for quasi-projective varieties, we can define regular and rational functions in a very similar way as the affine case. But here we just replace polynomials by homogeneous polynomials. So we have regular functions on quasi-projective varieties. So we start this with the definition. Let us take first some projective algebraic set. So let X be a subset of Pn, the projective n space. So this X be a projective variety. By variety here we mean it is irreducible. So be a projective variety. So let us take U to be an open subset of X. That means this U is a quasi-projective variety. So i.e. U is a quasi-projective variety. Now we can define the ideal of X, but now we are in the projective case. We have to take the homogeneous ideal of X. So let I of X be the homogeneous ideal of X. Now X being irreducible, then the homogeneous ideal of X is also a prime ideal, because we have proved this in one of the previous lectures. So now Ix being prime, it makes sense to define the coordinate ring of X. So the homogeneous coordinate ring, the homogeneous coordinate ring, let us call this Sx of X, is the ring uh, so this is the ring S, I mean the ring Sx is by definition given to be the quotient ring k x naught up to xn. Remember here we have to take n plus 1 variables. So modulo the homogeneous ideal of X. So this is the coordinate ring of X. Now the class of a polynomial, say f in the polynomial ring in n plus 1 variables in Sx. So this is denoted by the class of f. Again, Ix is an integral domain because X is a subvariety, quasi-projective subvariety. So Ix has to be, I mean, this X is given to be a projective variety, so Ix is a prime ideal. That means Sx is an integral domain. So let us make this a remark. Since X is since X, which is projective algebraic set, so since X is a projective variety, which means it is irreducible, the homogeneous ideal of X is a prime ideal, and hence uh, the coordinate ring of X is actually an integral domain. So this is an integral domain. Now we have one more remark here. So unlike the affine case, elements of Sx do not define functions on X. So let us make this a remark here. So unlike the affine case, elements of Sx, say they do not define, I mean they do not define functions on X, because if I look at the element f of lambda a naught up to lambda a n, this need not be equal to the element f of f evaluated at a naught up to a n. So this may need not be true. Now to get a well-defined function, one has to take the quotients. So now to get well-defined functions, uh, one has to take the quotients. I mean quotients h, which are given by f or g of classes of polynomials. Of same degree. So say D. So if this is the case, because then we can write, so because then if we look at the element f of lambda a naught up to lambda a n, or g of lambda a naught up to g of lambda a n, this is equal, so f and g being homogeneous polynomials of degree d, so we get lambda d f of a naught up to a n over lambda to the power d g of a naught up to a n. So this gives us well-defined functions. Now we have one more definition here. So let us denote the class of f, this little f by f, where this class is the element of the coordinate ring with this little f to be an element of the polynomial ring in n plus 1 variables. Now the homogeneous part of degree d of f is denoted by, so the homogeneous part of degree d of this f is defined as, so it is the class of the homogeneous degree d part of this little f. So note that this is well defined. So this definition is well defined. Note that this is well defined. Why? For uh, if we take, I mean, the class of little f to be equal to the class of little g, so that means the class of f minus g, this is an element of ix, the homogeneous ideal of x. So as this ix is homogeneous, so as ix is homogeneous, uh, It's a homogeneous ideal. So then uh, for all, then we have, so this is actually f minus g, not the class. So if this is the case, that means the degree d part of f minus the degree d part of g, this is also an element of ix. So this is true for all d, and this would imply, if I look at the class of this element, this is the zero class then, because this is an element of ix, or the degree d part, class of degree d part of f is same as class of degree d part of g. So now we call the set, so if we look at the set Sx, and we write here this little d, so if we let this set to be the degree d part of the classes of little f, where f is some element in Sx, we call this set to be the degree d part of Sx. Now, defining these things over here, we can now talk about the quotient field of Sx. Note that Sx is an integral domain, so we can talk about its quotient field. So let Q of S of x be the quotient field of Sx. Then the field of rational functions on x is defined as, so then the field of rational functions, we denote this field by kx. So this is the field of rational functions on x. So this is defined as, so this kx, it consists of those rational functions from the quotient field of Sx such that the f and g, they belong to the degree d part of Sx. So this is some, and this is true for some d, for some d. Now the element is in this field, they are called the, an element of kx is called the rational function on x.